The second drugs that can bind to the receptors are the antagonists. So as we have said before, antagonists, they have affinity to the receptor, but they have no intrinsic activity. That means they can produce no action. Therefore, what they do? They prevent the action of an agonist. How they prevent the action? By binding to the same receptor of the agonist, preventing the access of the agonist to the receptor. Just let us imagine that this is the receptor, and this is an agonist molecule, and this is an antagonist molecule. Each of them can bind to the receptor. If the antagonist molecule enters the receptor, the agonist will have no access to the receptor, and therefore its action will be stopped or disappeared. So, an antagonist will produce no action but prevents the action of an agonist. Okay? Now, there are two types of antagonists. First type is known as reversible competitive antagonist, and the second type is known as irreversible competitive antagonist. In the first type, the antagonist will bind with the receptor reversibly. That means the agonist can replace the antagonist from the receptor when it is present in enough concentration. That's why it's known as reversible competitive antagonism. And by competitive, what does it mean competitive? Means both the agonist and the antagonist, they compete on the same receptor. That means whoever present in higher concentration will take over the receptor. If the agonist is present in higher concentration, it will take over the receptor. If the antagonist is present in higher concentration, it will take over the receptor. That's why it is known as competitive antagonism, تنافسي. Okay? A second type is known as irreversible antagonism. In irreversible antagonism, once the antagonist binds to the receptor, that's the end of the receptor. That means the agonist cannot replace the antagonist from the receptor, whatever its concentration in the media. That's why it's known as irreversible antagonism. Okay? So, pharmacological antagonism, we called it pharmacological because the agonist and antagonist, they act on the same receptor. Okay? They are either reversible competitive antagonism or irreversible antagonism. Some people, they call it irreversible non-competitive antagonism. Actually, non-competitive competitive antagonism. I don't like this name because there is no mean of competition in this case. Okay? So we prefer to call it irreversible pharmacological antagonism. So how this type of antagonism will affect the response to full agonist? How they will change the dose response curve of a full agonist? That's what we are going to discuss in the few slides, next slides. So first, how a competitive antagonism will affect the dose response curve for a full agonist. Just let us imagine this is the dose response curve of a full agonist. A full agonist, as we have said, as we increase the dose, the response will be increased till we reach maximum. Once maximum is reached, any increase in the dose will produce no further response. This is a full agonist response. Suppose that the full agonist is acetylcholine. Acetylcholine, as we know, by acting on muscarinic receptor, for example, in the intestine, they produce contraction of the smooth muscle of the intestine. Therefore, as we increase the dose of acetylcholine, the contraction will be increased till we reach a maximum contraction. Then there is no any further increase in contraction. Okay? Suppose I added atropine, which is antagonist to acetylcholine muscarinic receptor, atropine. First, in high concentration. It is present in higher concentration. I added atropine first, then I started adding acetylcholine. What do you think will happen? What do you think will happen? At the very beginning, atropine is present in higher concentration at the beginning because we said it is a competitive antagonism. What does mean competitive? Both the agonist, the antagonist, they compete on the same receptor. At the very beginning, atropine is present in higher concentration. Therefore, acetylcholine will produce no response. But by increasing the concentration of acetylcholine, the response starts to appear slowly, and by further increase in the acetylcholine concentration, the response will increase till the point that acetylcholine can replace all atropine from the receptor, and it can produce a maximum response. So this is dose response curve of full agonist plus atropine. Of course, the actions produced by the full agonist, what atropine has done now. So this is full agonist plus atropine. Okay? Now, so what had happened, as we can see? We said that a full agonist has three major properties. The first, full agonist, what does it have? Have affinity, the ability to bind to the receptor. And we said it has an intrinsic activity. And we said it has a full efficacy equals 1. Okay? This is a full agonist. So let us start with the efficacy. Did it change efficacy? Efficacy is still 1. Efficacy, no change in efficacy takes place. Therefore, competitive antagonism did not affect efficacy. Okay? Now, in intrinsic activity, we said action. As we can see, the agonist still produce action, so intrinsic activity has not changed as well. So what has changed? Affinity changed. Affinity changed. How affinity is changed? If we look at the dose response curve, we find that the ED50 of the agonist alone, ED50 of the agonist alone, we call it B, for example, agonist alone, is smaller than the ED50 of the agonist in the presence of the antagonist. So what the antagonist has done, as you can see, this is the ED50, this is the ED50. Suppose this is 1, 2, 3, 4, 5, 6 milligram. Suppose, just a supposition. So in this case, what happened? The antagonist increased the dose needed to produce the same effect, to produce the same effect. Okay? Therefore, the antagonist increased the dose needed of the full agonist to produce the same effect. That means decrease in potency, because we needed more dose. When we talked about potency, we said potency reflects the dose. If the potency is high, the dose is less, and vice versa. In this case, we needed more dose, means that decrease in potency. So this is what competitive antagonists do. They decrease potency. Okay? Therefore, competitive antagonists, what they do, competitive antagonists, what they do, they decrease potency. Therefore, competitive antagonists, they decrease potency. This is the most important. Okay? Therefore, competitive antagonists, they compete with the full agonist on the same receptor, they decrease potency, and they produce shifting of the dose scale shifting parallel. Actually, it is a parallel shift of the dose curve, shifting of the dose response curve to the right. Dose response curve to the right. Okay, so you needed more of the you needed more of the agonist to produce the same response. Okay, and now, so I repeat, the competitive antagonist will decrease the potency of a full agonist by shifting the dose response curve to the left, to the right. The more the shifting to the right, the more potent is the antagonist. This is logic. The more shifting to the right, the more potent is the antagonist, as we can see. Okay? The more shifting to the right, the more potent is the antagonist. Let us take an example. Suppose we have two antagonists. Antagonist A, which is a competitive antagonist, and antagonist B. So this, for example, that we draw first, this is antagonist A. For example, antagonist A. Suppose I have antagonist B, another antagonist. I place the antagonist first and then started putting the agonist, increasing the dose of the agonist. At certain point, the agonist starts to produce a response and produce the dose response curve like this one. Okay, this is full agonist plus antagonist B. We said the more shifting to the right, the more potent is the antagonist. Now, which one you think is more potent? Antagonist A or antagonist B? Which is more potent? Antagonist A or antagonist B? Of course, antagonist B is more potent. Why? Because the ED50 needed from the agonist in the presence of the antagonist is larger. You see, the ED50 is larger. The ED50 needed of the full agonist to produce exactly the same response value, which is the 50%. In this case, it is larger than the ED50 needed in the presence of the antagonist A. This is larger ED50. Okay, that means antagonist B is more potent because decrease the potency of the agonist more. Okay, now, so a competitive antagonist will compete with a full agonist on the same receptor. Competition means that whoever present in higher concentration will take over the receptor. If the agonist is present in higher concentration, it will take over the receptor and vice versa. Okay? The antagonist, what does it do? The competitive antagonist? Competitive antagonist, we said it decreases potency, but it does not affect efficacy. Efficacy stays zero, i.e., the agonist can still produce maximum effect in the presence of the antagonist, but you needed higher concentration. This means the dose response curve of the full agonist will be shifted to the right, and this shifting usually it is parallel and with the same slope. Okay, so this is the first type of pharmacological antagonist, which are competitive antagonists. The second type of pharmacological antagonists are the irreversible antagonism. Irreversible antagonism. And by irreversible antagonism, as we have said, and now once the agonist bind to the receptor, that's the end of the receptor. The receptor, like it is deaf, it is not there, like it is not there. Okay, so just let us imagine this is the dose response curve of a full agonist alone. First, this is a full agonist alone. Okay, so by increasing the dose of the agonist, response will increase till we reach maximum, till we when once it reaches maximum, that's the end. Okay, suppose let us to make the thing easy for us to understand, let us imagine that there are 100 receptors, 100 million or whatever. Just for example, it is hypothetical assumption that we have 100 receptors, okay? And the agonist to produce maximum effect, it need only the agonist to produce a maximum effect, and the agonist to produce a maximum effect, it needs only 10 receptors to produce maximum effect. Okay? So we have 100 receptors in the media, and the maximum effect produced by the agonist can be done by occupying only 10 receptors. Okay? Suppose I place the antagonist first. I put the antagonist at the receptor. And the antagonist blocked 89 of the receptor. That means 89, once they are blocked, that means end of the receptor. Like if they are not there. So 89 blocked. So how much is left out of 100? 11. 11 receptors are left from the 11 receptors are left from the total. So in this case, if I add agonist, what I will see? If I add agonist, I will see that by increasing the dose, the response will be increased, and we still see a maximum response. We still see a maximum response. Why? Because we said maximum response can be achieved by the agonist by occupying only 10 receptors. In the media, there are 11 receptors available. So the agonist can still produce maximum response. Okay? This is the first assumption. Okay. Now suppose I place the antagonist. I put the antagonist first, and the antagonist blocked, for example, 93 of the receptors, of the total receptor. Blocked 93 of the available receptor. So what will happen? 93 finished as if they are not there. So how much is left in the system? Only 7 receptors available for the agonist. So what will happen in this case? The agonist can never achieve the maximum response. So what will happen? The agonist, as increasing the dose of the agonist, response will be increased, but can never reach the maximum response because what is available is only 7 receptors. That means I will get only 70% of the maximum response. Okay, I repeat it again. Now, I place the antagonist at the receptor. The antagonist in concentration enough to block 93% of the receptor. How much is left? Only 7%. So in this case, then the agonist, when I add the agonist, I will see an increase in the response till we reach a point when there is no further increase in the response. This is the maximum I can reach, which is not the natural maximum that I can attain. Okay? Okay. Now, suppose I added more of the antagonist, more dose of the antagonist that blocked, for example, 97% of the receptor. So how much is left free? Only 3% of the receptor left for the agonist to produce action. So what will happen in this case? I will see that the agonist can produce only 30% of the expected maximum response. 30%. Okay? So what do you think happened in this case? We said that the agonist have affinity against property. It has an affinity, it has an intrinsic activity, and it has what? Efficacy. Efficacy of full agonist is 1, as we have said. So what happened to the efficacy by the antagonist? Is it the same ولا decrease the efficacy؟ حصل decrease in the efficacy. This is 1. This is the first. Therefore, a reversible antagonist will decrease the efficacy of the full agonist. Efficacy of the full agonist decreased. Intrinsic activity is still there, of course, still can produce action in the presence of the antagonist. And the affinity decreased, like it's not that important. Even the affinity, as you can see, the shift of the dose response curve to the right. Not very strong shift as we have seen with the competitive antagonism, but still some shifting of the dose response curve to the right. Okay, that means we need a larger dose of the agonist to produce the same effect. Therefore, the most important effect of the reversible antagonism that they decrease the efficacy of the agonist. As we can see, the more the decrease in the efficacy of the agonist, the more potent is the antagonist. Okay, then therefore the more the decrease in the efficacy, the more potent is the antagonist. This we should remember. The more potent the antagonist, the more the decrease in the efficacy. Okay? So the more the decrease in efficacy, the more potent is the antagonist, which is, as we have said, they are irreversible antagonism. Okay? Now, if I have given the choice of selecting an antagonist, which one you think is preferred clinically? Competitive antagonism or irreversible antagonism? Which is more preferred clinically? Which one I should choose when I given the choice of two drugs, competitive antagonism and irreversible antagonism. I will choose competitive. I will choose competitive antagonism. Therefore, most drugs which are used clinically, they are competitive antagonism. Why? Why competitive antagonism is better? Why? Why? Because competitive antagonism, suppose I have given, like for example, let us take example, propranolol مثلا. Propranolol is a beta blocker, beta receptor blocker. It is a competitive antagonism. It is beta receptor blocker. It is a competitive antagonism at beta receptors. So if I give an overdose of propranolol, I can overtake it by giving an agonist, for example, adrenaline. For example, it's not usually common practice, but at least to explain my point of view. So in competitive antagonism, I can reverse the toxicity of the antagonist by giving an agonist. This is uncompetitive because both they compete on the same receptor. Okay? Then competitive antagonism, I can reverse the toxicity of the antagonist by giving enough dose of the agonist. This cannot be done in case of irreversible antagonism. Irreversible antagonism, once you give the dose, that's the end of the receptor, and you need many days before new receptors are sensitized. Okay? So this is the antagonism as a ligand, pharmacological antagonism. Ligands, either they are irreversible or competitive. So what we have discussed up to this point, what we have discussed in summary, we said that drugs bind to the receptor. They are either agonist, like full agonist or partial agonist, or they are an antagonist. They are competitive or irreversible. We also spoke about the type of responses produced by an agonist, which are either a graded response or quantum response. Okay? Now, in our next presentation, we are going to talk about drug-drug interaction. If I take more than one drug at the same time, what will happen? So we'll talk about the antagonism, if one drug antagonizes the effect of the other, and we will speak about the different type of antagonism, including chemical, physiological, and pharmacokinetic antagonism. Also, we talk about the potentiation and synergism, inshallah. I would like to thank you very much for your attention. If you like the presentation, please don't forget to press like. Please subscribe to my channel. I wish you a good health and prosperity. Stay in peace. Wassalamu alaikum wa rahmatullahi wa barakatuh.